Hi everyone, I hope you're enjoying the conference so far. My name is Matthew Cao, and today I'm going to talk to you about online hypergraph matching with delays. This is joint work with Marco Pavone and Amin Sabri from Stanford and Max Schiffer from TU Munich. So the main motivation for this project is in ride sharing. Now, ride-hailing services have become central to transportation all over the world. In the United States, there's Lyft and Uber. In China, there's Didi. And in Southeast Asia, there's Grab. Because of this, there's been a lot of incentive to find ways to maximize the efficiency of shared rides and ride sharing so that the transportation system is as efficient as possible. And there's been a lot of work on studying ride sharing from a graph matching perspective, where vertices represent customers, and the goal is to pair users together by choosing a matching in a certain graph. Okay. But in practice, ride-hailing vehicles have capacity more than two. So we can think about a more general problem where we're trying to bundle groups of 3, 4, maybe even 5 customers to share a vehicle. And this is the motivation for studying high-capacity ride-sharing. So the ride-sharing problem in words is as follows. There's n customers that submit requests for transportation sequentially to a platform, like a ride-hailing platform. And the platform has service vehicles of capacity K, right? And so a ride-sharing strategy is thus a partition of the customers into groups of size at most K, where all of the users in a group are going to be served by the same vehicle. Now, ride-hailing is a on-demand service, so the system has to respond quickly. And for this reason, we have this setting that customers must be matched shortly after their request time or abandoned, right? And this is slightly different than typical online algorithms literature, where a decision must be made immediately once a request arrives. Here we're allowing a short delay for the system to gather more information. And finally, as is standard in online algorithms literature, decisions are irrevocable. So once it is decided that a certain group of users will share a ride, you cannot take that back. Okay. Now, mathematically, we're going to formulate this problem as an online hypergraph matching with delays, right? So the instance is going to be given by a weighted hypergraph where the vertices represent customers and the edges represent groups of customers that can be efficiently served by a single vehicle. As we said before, the number of vertices in an edge is at most K, which represents vehicle capacity constraints. And the edge weights are going to represent how efficient such a grouping is. And we'll get to this, what exactly it means later. As we said before, ride-hailing is an on-demand service, so we're going to look at this hypergraph matching problem from an online perspective. So vertices arrive sequentially. An edge is revealed once all of the vertices in it are revealed. And to model this utility for weighting, an edge must be matched within d time steps of its arrival. Equivalently, 2 customers can share a ride only if they arrive within d time steps of each other. Okay? And here, d is like the arrival rate of requests. We can think of this as saying, look, if the platform promises to match a request within 1 minute of it being submitted, then d is going to be like the average number of requests that the platform gets within that 1 minute interval. So d is a sort of measure of how popular the platform is. So if the platform is very popular, d could actually be very big. Okay? And as we said before, decisions are irrevocable. And here, based on this formulation, a ride-sharing strategy which chooses which users to share rides is equivalent to finding a matching in this hypergraph. Okay? So in this talk, we're going to be focusing on utility maximization, which we're going to call the online KD max matching problem. Here, the weights of the edges represent utility, for example, the profit of the platform from doing this carpooling. And the goal is to find a matching with large weight in this online setup. In the full paper, we also discuss cost minimization variance, but for the sake of time, in this presentation, we're just going to focus on utility maximization. The evaluation of algorithms is going to be based on competitive ratio. So for utility maximization, the competitive ratio is a number between 0 and 1, which says how much of the optimal utility can you promise you will get. Okay, cool. So there's a lot of related work on these online algorithms where the algorithm gets a little bit of time. There's a little bit of delay between when a request shows up and when it needs to be fulfilled. So Ashlagi et al. Studies a special case of our model for the setting where k is 2. So the hypergraph is actually just a graph, right? And there are other works that look at matching in random graphs where the amount of time a request stays in the system is a random quantity instead of being exactly d, as is in our case. Okay. In the k bigger than 2 setting is fairly related to online resource allocation. And typically these works think about instances where there is some structured randomness, right? So in secretary problems, the arrival order of requests is uniformly at random. And there's also some other works by Ma et al., which study what happens if you know the full distribution of the requests, right? But sort of our role here is twofold. We want to sort of take the results from online matching and generalize them to k bigger than 2, so hypergraph matching. And for with respect to online resource allocation, we want to see if we can get results that hold in a competitive analysis perspective where we don't make distributional assumptions on the inputs. Okay, so with further ado, let's start talking about utility maximization. We have two main contributions for this area. First, we present a randomized batching algorithm, which we prove runs in polynomial time and has a competitive ratio of 1 over d. And just to remind you, d is the number of time steps that the algorithm has to match a request. Okay. We also prove that when k is at least 3, no algorithm can have a competitive ratio better than 1 over d. So this establishes 1 over d as the optimal competitive ratio, and that it can be achieved using computationally efficient procedures. The outline for the rest of this talk is going to have this structure. First, we're going to talk about how a procedure that allows us to convert methods for the offline hypergraph matching problem to our online hypergraph matching problem. Now, this still has some issues, and it turns out that edges in the optimal matching with very large diameter are going to sort of not behave well under this offline to online conversion. We need to address that, and then once we address that, we'll get the desired optimal polynomial time competitive ratio. And then we'll conclude by discussing a hardness result, which basically proves that no algorithm can do better than 1 over d by discussing some variants of the secretary problem. Okay? Right. So perhaps unsurprisingly, our online hypergraph matching problem is intimately related to the offline hypergraph matching problem. So one idea we can think of is it possible to take an offline algorithm and convert it into an online algorithm? And perhaps the natural way to think about doing this is via batching, right? So in batching, we take the online instance, we cut it up into batches of size d, right? And then we run a offline matching algorithm for each of the batches. And here, the batches are of size d because, you can still match the first vertex in the batch before it expires, and you get to see the last vertex in the batch since there's d of them. Okay, but this doesn't quite work because, for example, in this image, if there are some edges, which are shown in red here, that don't lie entirely in any single batch, then batching may miss them. And if these red edges have very large weight and the blue edges have very small weight, then batching is not going to be competitive. Okay. But fortunately, this can be fixed using randomization. So here we introduce the Randomized-Batching algorithm, which does the following. It chooses a shift parameter, z, uniformly at random between 0 and d minus 1. It shifts the batches by the start and end times of the batches by this z. Okay, so instead of the ith batch starting at time step I times d, it starts at I times d plus z. And then now we just apply an offline algorithm A within each batch. So just to give a visual representation of why this might work, let's revisit that previous example. So in the top picture, the red edges are not contained in any batch. So it's possible that batching may miss these edges. But there is some value of Z for which, the shifted batches will contain these red edges, right? So there should be some probability that every edge will be seen by the algorithm. And therefore, that should lead to a positive competitive ratio. Concretely, we have the following result. So let A be an algorithm for the offline hypergraph matching algorithm, or hypergraph matching problem, with competitive ratio rho of A, right? Then randomized batching produces a matching with this performance guarantee, right? So the expected weight of the matching we get is lower bounded by the competitive ratio of A times the weight of the optimal matching, where each edge is sort of downweighted by something proportional to its diameter. Okay, so in particular, if all the diameters of the edges in the optimal matching are small, then randomized batching will do very well. Okay, so let's prove theorem 1. So one of the first main ideas we're going to need is the following observation. So what's the chance that any edge is going to be contained inside a batch? So what I mean when I say an edge is contained in a batch, we just mean all of its vertices are contained inside of a batch, right? And this probability we claim is D minus the diameter of the edge divided by D. And I have prepared a small picture for you here to show why this is the case. So without loss of generality, we can assume that the last vertex in the edge is time step D minus 1. We can always, do a linear change of coordinates to make this true. And from here, we see the following. If Z is 0, right, then all of the edges between the red bars is going to be contained inside of a batch, right? Similarly, if Z is equal to D minus 1 minus the diameter of E, then all of the nodes between the blue bars are going to be contained inside of a batch. So any Z between 0 and D minus 1 minus diameter of E will have all of the nodes in this edge contained inside a single batch, right? So there's D minus diameter, many values of Z, for which this edge will be in a batch. And since Z is chosen at random, this is the probability, right? Cool. Once we have this, let's sort of reason about what's going to happen in randomized batching. So if M is the matching produced by the algorithm, we can write M as a union of MI, where MI is the matching produced by the ith batch, right? So here what we see, the first inequality here is due to the competitiveness of A, right? So the weight of MI is at least the rho of A times the biggest matching that you can get inside batch I. And this is certainly bigger than the set of all the edges of the optimal matching that happen to land in batch I, right? So once we have this observation, we can use linearity of expectation to do some algebraic manipulation here to conclude this. And now the expectation of an indicator is just the probability, right? So this is equal to the probability. So this is equal to a sum over the weights of the edges in the optimal matching times the probability that the edges are in a batch, right? And we know what this probability is, so make the substitution, and that proves the theorem. Okay, so some implications, right? The diameter of all the edges in the graph, in the hypergraph, are at most D, right? That's by the constraint that no user can be matched after D time steps after it arrives, right? That's the online constraint. So using that inequality, we see that randomized batching using an algorithm A is rho of A over D competitive for the online hypergraph matching problem. So this basically says any algorithm for the offline hypergraph matching problem can be turned into an algorithm for the online problem by paying a factor 1 over D in the competitive ratio. But the next question you should ask is, well, how good are the offline algorithms for hypergraph matching? So the known results for rank K hypergraph matching, and here rank K just means that the biggest number of nodes inside an edge is at most K, right? So we know there's a greedy algorithm that is 1 over K competitive, and it runs in nearly linear time. This is near optimal because it's also been shown that it's NP hard to approximate this problem better than log K over K, right? So greedy is optimal within a factor of log K. What does this mean for our problem? Well, if we choose A to be greedy, then randomized batching is 1 over K D competitive, right? And if we use an optimal offline matching algorithm which has rho of A equals 1, then randomized batching is 1 over D competitive. Okay, cool. With this in mind, let's discuss the hardness result, right? So our hardness result says that when K is at least 3, no algorithm can have a competitive ratio better than 1 over D for online KD max matching, okay? And we prove this in 2 steps. The first step, we introduce something called the adversarial secretary problem with D applicants. Here it's abbreviated DASP. And we show that it is a special case of our online matching problem, right? In the second step, we show that the optimal competitive ratio for DASP is 1 over D. So that's going to establish that nothing can do better than 1 over D for online max matching. Okay? And formally, what is this adversarial secretary problem? Well, it's as follows. So there's D applicants for a secretary position, and they each have some non-negative aptitude score. At most, 1 applicant can be hired, and the ith applicant's aptitude is revealed in the ith time step, and the ith applicant can only be hired in the ith time step, right? And so the goal is to maximize the aptitude of the secretary you hire. If you're familiar with the regular secretary problem, the only difference here is that instead of having a random arrival order of the secretaries, this has an adversarial arrival order, okay? Showing step 2 is actually fairly simple. It's based on an induction argument, right? So there are 2 things that can either happen at the first time step in the adversarial secretary problem. Either you hire the first secretary and the game ends, or you do not hire the first secretary, and now you have to solve an adversarial secretary problem on the remaining D-1 applicants, right? So using this induction, it's not hard to show that the best competitive ratio is 1 over D. So all that remains is step 1. And to prove step 1, what we do is the following. For every instance of the adversarial secretary problem, we construct a hypergraph so that the hypergraph matching problem on such a hypergraph is the same as the adversarial secretary problem. And this is kind of what such a hypergraph would look like. So there's 1 edge for every applicant, okay? And each edge has 3 nodes. The first node, or the earliest node, dictates when the edge will when the edge will expire, right? Because an edge can only be chosen before any of its vertices have waited longer than D time steps, okay? The last vertex in the edge sort of hides it controls when the weight of the edge will be revealed, right? So recall that an edge weight is revealed once all the vertices arrive, okay? So the fact that the first vertex and the last vertex of these edges are spaced exactly D apart means that these edges can only be chosen in the time step that they are revealed, okay? Oh yeah, I forgot to say, this is the graph evolving in time. Vertices are arriving on the right, and vertices are leaving on the left. And a vertex is red when it is about to leave the system, right? On the last time step that it will be in the system. And so this is as it evolves in time, okay? And finally, all of these edges have a non-zero intersection, right? They all contain the node 8. This means that at most 1 of the hyperedges can be chosen in a matching, okay? So just reviewing, the first and the last vertices in the edges make sure that the weight is revealed in the same time step as the edge is about to expire. This means that the weight of the edge is revealed, and only in that time step can you choose, can you pick this edge into your matching. And the second property is that all of the edges intersect each other, so you can only pick one edge to be in your matching. And this is why this type of graph encodes the adversarial secretary problem. Okay, cool. So let's just recap a little bit what we've done so far. So based on the hardness result and on the performance of randomized batching, we can conclude that 1/d is the optimal competitive ratio. In particular, randomized batching using an offline algorithm A with a competitive ratio of 1, so something that can compute a maximum weight hypergraph matching, will get you the optimal performance for online hypergraph matching. But it's NP hard to get a competitive ratio better than log k over k, right? So, if D is very big, right, the system's very popular, then, simply running this approach up here is going to be very computationally expensive. So let's fix this. Let's get a polynomial time algorithm that is 1/d competitive. So one thing we want to remember from Theorem 1, we get this performance guarantee, right? So what we see here is that basically edges with large diameter contribute less of their weight to our lower bound, right? And so we need to fix this in order to get a better competitive ratio. Okay, let's do that. So there are two cases to consider. Let's figure out what's wrong with the current setup first. There are two cases. The first case is when you look at all the edges that have diameter at most d minus k. And the second case is when you look at the edges with diameter more than d over k, or d minus k. Okay. Let's say we're using a greedy algorithm, so rho of A is 1/k. Here is what the guarantee of Theorem 1 gives us. Okay, now we're just going to split the sum over edges in opt with diameter that are small versus diameter which is big. Okay, and here we can lower bound this by 1, and here we can upper bound this by k, right? So we do that, and then what we see here is the following. The edges with short diameter, they're already giving us, 1/d of their weight, right? The problem is here, right? The problem is that the long hyperedges are giving us 1/kd fraction of their weight. So we need to fix this component to make sure we can get a 1/d competitive algorithm. And that's what we're going to do. Okay, and the main observation here is the following. For an edge in a batch, I, if the diameter of the edge is bigger than d minus k, the batch's first k vertices. Okay, and this is easily explained by the following picture, right? So this is a batch, right? It contains d vertices, 0 to d minus 1. If you don't contain any of the first k vertices, then you're a subset of this set. But this set has diameter d minus k, right? So in order for you to have to have diameter bigger than d minus k, you have to touch at least one of these k vertices, right? But as a result, this implies that each batch can contain at most k edges from the optimal matching that have diameter bigger than d minus k. And we're going to use this to our advantage to get a nice algorithm. Okay, so let's just set up a little bit of notation first. So let m be the number of edges in batch I. Okay, and let script m be the set of matchings in batch I where every edge in the matching has the diameter at least d minus k. Okay, based on our previous observation, the matchings in script m can only have up to k edges. Therefore, we can bound the size of m using this expression. What's important to notice here is that for small constant k, like 6 or 7, this is polynomial in the number of edges in the batch, right? So that's what we're really looking for. So once we have this, we can describe the depth k greedy algorithm, right? So what it does is, given a batch, it looks at all of the matchings m inside script m, and for each of them, it adds edges to m using a greedy algorithm to obtain some m bar, right? So basically you extend M to a maximal matching. Okay. And then over all of the maximal matchings you obtain in this way, you return the one with the largest weight. All right, that's what it does. And it's important that the size of script M is small. It's only polynomial in the size of the number of edges in order for this thing to run efficiently, right? If this was exponentially large, then this would not be a polynomial time algorithm. Okay, so just what does this mean? So if Mi is a matching produced on the ith batch by this depth k greedy, then its weight is, this should be bigger than the max over M, the weight of, right, this matching, right, plus, so we applied greedy to the rest of it, right? We extend this matching using greedy. So, the weight of this matching is at least 1 over k times the biggest possible matching, M prime, so that M union M prime is a matching in the whole batch, right? Okay, well, since and basically you can show that M star is a member of script M. And so we can get this inequality. And this is really what we're looking for, right? So once we have this, how does this help us, right? So let's think about what happens if M is the result of randomized batching using A to be this depth k greedy. Using very similar calculations to what we did in the first part, now we replace the weight. We apply the lower bound we just got, right? Do some linearity of expectation stuff. We get this here. And importantly, the 1 over k in front of the long edges here, the edges with larger diameter, is now gone, right? And so once we have that, we can simplify terms, and this will give us that the expected weight of M is at least 1 over D times the weight of the optimal matching. Okay, cool. So just putting it together, this theorem just summarizes what we just talked about. Randomized batching with A equal to depth k greedy is 1 over D competitive for our online matching problem, and it runs in time order number of edges to the power k plus 1, right? And so for k as is constant, this is polynomial in the size of the input hypergraph. Okay, so in conclusion, we propose an online KD max matching problem, which is motivated by high capacity ride sharing. We then presented a randomized batching algorithm and proved that it has the optimal worst case performance and it runs in polynomial time. We also address cost minimization frameworks in the paper that we didn't talk about in the presentation. Future work, there are 2 main areas we're thinking about. First, are there application-specific assumptions of ride sharing that we can impose onto the hypergraph to improve the set of achievable competitive ratios? And secondly, it's related to tolerance of the system to cancellations, right? So it can happen, in particular in practice, when users get a carpooling ride and they cancel it because they don't like it, right? And then the algorithm needs to still be able to serve the rest of the customers and try to maximize its utility that way. So thank you for listening. I look forward to any potential questions and discussions we have during the conference. My contact information is here, and you can find the full paper here. Okay. I hope you enjoyed the talk, and